Hello everyone. In this video we will continue to examine topic 5.2, the heating effect of electric currents, and in particular we will continue to unpack multi-resistor circuits, focusing on those in parallel. So in the last video we ran through what Kirchhoff's first and second law had to say about a simple series, a multi-resistor circuit with resistors in series. So we're going to do the same thing for parallel here. So consider this simple parallel circuit. Okay, remember that parallel means that the resistors are connected on both ends. And as a result, sort of apply Kirchhoff's first law to this particular case and Kirchhoff's second law to this particular case. Well, Kirchhoff's first law says that for each of these junctions here, the current through the battery is equal to I1 plus I2. So when the current splits at junction 1, I battery splits into I1 and I2, and when it rejoins as I1 plus I2. So in general, we can sort of extrapolate this and say that for any two circuit elements wired in parallel, the currents through those elements add, okay, and they add at the junction. Then apply Kirchhoff's second law. Kirchhoff's second law says that for any closed loop, okay, around the circuit, the EMF is equal to the potential difference. So the total sum of the EMFs is equal to the total sum of the potential drops around that particular loop. As discussed before, this results for the simple parallel circuit in the equation that the EMF is equal to the potential drop across both of these elements, labeled simply as delta V. So for circuit elements wired in series, the potential differences across them, that should say parallel, whoops, across them are the same. We are in trouble. Give me 1 second. I'm going to fix this live. All right. Then we're going to look at the general parallel relationships, okay? So in general, for currents in parallel, then the total current is equal to the sum of the currents through each of the branches of the parallel circuit. So this is just an arbitrary number of resistances, R1, R2, ... Rn in parallel. So if these resistors are in parallel, then the current through each of them will add up to be the total current sort of entering that particular part of the circuit or exiting that particular part of the circuit. So I2 total is the sum of the I sub i's. Similarly, if we look at each of the individual potential differences, delta V1 is going to be equal to delta V2, which is equal to ... delta Vn. So there's only one potential drop, or the potential drop is the same across each of the branches. Notice that this pattern, okay, is exactly opposite the series relationship. Okay, so the currents and the potential differences behave in exactly opposite ways between the multi-resistor circuits in series and the multi-resistor circuits in parallel. So as mentioned in the last video, what I would encourage you to do before we sort of move on is to have a try at figuring out what that means about the equivalent resistance of this mess right here. Okay, so what resistance would you need to replace R1 and R2 with to get the same total current through the battery? That's your question. That's the question I will get to in one moment. Notice that last time we managed to derive that relationship using Kirchhoff's first and second laws and the definition of resistance. So feel free to pause the video now if you'd like to look at that. And all right, so if you were to replace the two resistors in parallel with an equivalent resistance Rec to achieve the same current I, such that the equivalent resistance is equal to the EMF over I, what should the equivalent resistance be? Right, so we're moving from this circuit to this one. How do we keep I the same? Well, the first thing to note is that for this parallel circuit, the I coming out of the battery is equal to I1 plus I2, the two currents through the two branches. And we can use this plus the definition of resistance So note that EMF over the equivalent resistance, whatever that will be, is equal to delta VI over R1 plus delta V2, not delta VI, delta V1 over R1 plus delta V2 over R2. Okay, so this is just applying the definition of resistance to each of these terms. Then we can note that for resistors in parallel, and in general, we can move from sort of any EMF to a delta V here. All of these things are the same. So if these resistors are in parallel, the EMF is equal to delta V1 is equal to delta V2. So delta V, and delta V can be substituted in for each of these variables. But if they can be substituted in for each of those variables, they can also be canceled out. And that gives us our fundamental relationship here. So 1 over Req is equal to 1 over R1 plus 1 over R2. And so our general parallel relationship is just that 1 over the equivalent resistance is equal to the sum of 1 over all of the individual resistances. So 1 over R1 plus 1 over R2 plus ... 1 over Rn for an arbitrary number of resistors. This is generally true, and this is how you calculate the equivalent resistance for a couple of resistors in parallel. We will need to practice this moving forward. This is probably the trickiest relationship of all of the ones we have covered so far.